You know from prior videos or prior knowledge that if we have a list of terms that all follow the same pattern, that we call this a sequence. Now this list of terms, it could be shapes, it could be just a set of numbers, but if it's just a list and it follows that same pattern from one term to the next, then we call it a sequence. If we were to go a step further and add each of these terms together up to a certain term number, then we call that a series. So a series is simply the sum of the values of a sequence. Okay? So that will go from your first term to some other number, or for a set of terms within that sequence. So one way that we can write this, there's a couple different ways, but one way that we can write this is using sigma notation. Sigma is a capital Greek letter, and we use this along with u of I, n, and I equals 1 or I equals some number. So this is kind of how it's written in a general form, and then we'll look at a specific form in a second here. But what this all means is that first we have this sigma thing, and that means to sum it all up. That means what you're basically just means to add up this whole sequence, or add up this whole series. The u of I is the function that you're going to use within this series. I equals 1 is going to be what term number you are starting from when you are adding up the series. So what term number you're starting with, and the n is what term number you are adding up to. So how far in the series or sequence you are going to. All right. So if you want to kind of summarize this whole thing in a sentence, we can say that it's the sum of all of the terms, okay, from I equals 1 to I equals n, whatever that is, using the function u of I, right? So this is kind of the way that we read this sigma notation, using the sum of all the terms from I equals 1 to I equals n, using the function u of I. So let's look at a specific example. That might help a little bit. So let's say we're looking at the sum of all of the terms from k equals 1 to k equals 3 using the function 5 plus 2k. Okay? So what we're going to do is we've got 5 plus 2 times 1. So we're just taking k equals 1, drop it in there into that function, and that's our first term. That would be the first term of the sequence or the series. The second term is 5 plus 2 times 2, right? That's our second term. We're just taking k equals 1, take k equals 2, and then even k equals 3. 5 plus 2 times 3, and that's our third term. So now we use that function to use each of the terms from k equals 1 to k equals 3 to come up with values. And those values are 7 plus 5 plus 2 times 2, that's plus 9, plus 5 plus 2 times 3, that's 11, and when we add it all up we get 27. So that's the sum of all of the terms from 1 to 3 using the function 5 plus 2k. Alright, so you may want to write down this general notation, or maybe the blue sentence here in your notes to kind of keep track. We're going to go to a couple more examples real quick so you can see how this can be worked with in a couple different ways. But let's just make note of that for yourself, okay? So, a new example. We've got the sum of all the terms from t equals 3 to t equals 8 using the function 2 to the tth power. Okay? So, this is a little different because now we're going from t equals 3. So we're not going to use the first two terms in the sequence, or the first two terms in the series. We're going to jump right in at 3, and then we're going to go up to 8. So this is going to look like 2 to the 3rd plus 2 to the 4th plus 2 to the 5th plus 2 to the 6th plus 2 to the 7th plus 2 to the 8th. Right? So that's all that means. So we're starting with term 3, not term 1, because t equals 3. We go up to the 8th. So then again, it's just a matter of computing each of these numbers. So we've got 8 plus 16 plus, 32 plus 64 plus 128 plus 256. And you can check my math, but I think that that all adds up to 504. Okay, so that's kind of a way that you can do this. So your t value doesn't have to start at 1 all the time. It can jump around there a little bit as well. Another way you might use sigma notation is to try and summarize a series. So what we're going to do is we're going to write the summation using sigma notation for 3 plus 15 plus 75 plus 375 plus 1875 plus 9375. Okay, so before we can get right to the sigma notation, we have to kind of break this down a little bit. So what I like to do is I like to list out all of my terms. So I'll say term 1 is 3, term 2 is 15, term 3 is 75, term 4 is 375, term 5 is 1,875, and term 6 is 9375. So what I'm going to do is I'm going to look to see if there's any kind of common difference or common ratio in this. And for me, the first few kind of jump out. It's easier with the smaller numbers to see, but when we go from 3 to 15, we're multiplying 3 times 5 to get to 15. And when we take 15 to get from 15 to 75, we're going to multiply 15 by 75. And 75 times 5 is going to be 375, and so on. Now another way you could do this is like we've done in previous videos. You could take 15 divided by 3 and see if there's a common difference or ratio there. 75 divided by 15, see if it matches up. 375 divided by 15, and so on. So you can check it that way as well, using your division going from n plus 1 divided by n, u of n. Okay, so you can also use that method. And again, keep in mind it could be arithmetic, so you might want to check that also to see if there's an add or subtract values in there. But this one kind of jumped out easily at us as a geometric. Okay, so with all of that, now let's see if we can find some kind of pattern within here where we can write it in a general notation. So I'm going to start by saying t of 1 equals 3, all right? Just kind of rewriting it here. T of 2 then is t of 1 times 5, right? We knew that. That's kind of using our recursive formulas here. So t of 3 is t of 2 times 5, but we can also say, well, t of 2 is the same thing as t of 1 times 5. So let's plug that in for t of 2, and we can get t of 1 times 5 times 5, or t of 1 times 5 squared. Now, you could write 25 in here, but I generally don't expand out when I'm doing this because I want to see if there's any kind of pattern that emerges, okay? And if you have it written out as t of 1 times 25, you might not see the pattern, so I leave it in exponential form. So let's look at t of 4. T of 4 is t of 3 times 5, which we now just said is the same thing as t of 1 times 5 squared. So I'm going to plug that in, and I get t of 1 times 5 squared times 5, which is t of 1 times 5 cubed. Now you might start recognizing a pattern here. I'm starting to see one. So if we look at this, we've got t of 1 times 5 cubed, right? So we've got here term 3 goes to 5 squared. Term 4 goes to 5 cubed. And even if we look back at term 2, we could say term 2 was to 5 to the first power, right? We didn't write that, but we know that that's there. So we can come up with a general formula without even having to go to 1875 and 9375 by saying that t of n is going to be t of 1 times 5 to the n minus 1 power. So let's start putting this into our sigma notation. We're going to go from n equals 1, and let's see, how many terms do we have here? 1, 2, 3, 4, 5, 6. So we got sigma to the 6, and we're going the first term, which is 3, times 5 to the n minus 1 power. Now, I've got this formula, but let's make sure that this works. So we've checked it all with everything except that first term. So t of 1 is 3 times 5 to the 1 minus 1 power, right? That's the n minus 1 power. So that comes out to be 3 times 5 to the 0 power. Remember, anything to the 0 power is 1, so we end up with 3, so that works. So our general formula then is going to be the sum of all the terms from n equals 1 to n equals 6 of the function 3 times 5 to the n minus 1 power. Okay, so that's how you can kind of use a series that's listed out for you to come up with a general notation. So hope that helps kind of summarize this method. We'll look at other methods on how to write series, a different notation to write series that's similar to how we write sequences in the next video. So we'll talk to you then.